Hey everyone, thanks for coming to our talk. We might be keeping you between lunch, so hopefully we don't drown on too much. So we're going to talk about validating GPUs and NICs, or GPUs and networking, or AI accelerators, depending on what you want to call them, XPUs, Broadcom likes to use, without clusters, which is really hard because fundamentally you need a cluster. So this work is on behalf of what we've done at Meta, myself and a few of my colleagues. Arvind couldn't make it today, but there's multiple people behind us. Ashutosh is going to talk from Keysight. There's tens of people behind him, so I want to thank everyone who contributed to this. So this is somewhat of a continuation from the talk we gave in 2023. 2023, we talked about evaluating the performance of all-to-all collectives on our Xeon systems. It was much harder than we thought when we started. It started with, okay, the performance isn't anywhere near roofline, what do we do about it? Ultimately, we dug into the collective state machine, how the network was configured. We built a complex test bed with multiple racks. In the end, we had to drill into packet captures because we're getting switches from the signals from our switches that indicated that the buffers were filling up. We drilled in further. We saw incast. Incast was due to microbursts, and ultimately it was very complicated. So one of the call to actions there is, how do we do it better? In that test bed, we were limited by a few racks, and it was very hard to measure. How can we go about this a different way? So that's kind of the subject of this talk. So there has to be a better way than we did last time. So we worked on it internally, we collaborated with Keysight, and this is what we came up with. Normally in a collectives test, you have a bunch of nodes. By definition, the job of the collectives is to exchange data between them. But there's no reason why you have to simultaneously test every NIC and accelerator. So the idea here is to focus on testing one NIC and one accelerator and mock everything else. So imagine a magical device that can behave just like your switch or just be like your rack. Think of it as a hardware collectives emulator or a traffic generator, whatever you want to call it. And instead of doing a cluster level test, you reduce your sort of cluster under test to system under test or even device under test. And then there's some questions there's no perfect answer to. It's like when I'm testing a NIC and an accelerator, do I also test the network? The switch, the signaling from the switch is fundamentally part of it. So we look at it both ways. We're going to both present data on a system under test with just mocking different endpoints, and just a device under test, just the accelerator and the NIC by itself. And there's one other thing I want to talk about. One of the complexities that we talked about last time is how the collective communications library works. So we went over the collective state machine, how buffers are exchanged, and that was actually a contributing factor to some of what we were seeing with incast. So in these results, we replaced the vendor CCL with our own. We have our own collective communications library. At least for all-to-all, it's very simple. So we wanted to reduce one factor from the equation. So what are we calling this? We're calling this one-arm AI validation, or one-arm testing, whatever you want to call it. One-arm something, right? The idea is you mock, like I said before, everything but the device under test. And you might think, how is this possible? How can I make my device running a complex collective algorithm or an AI workload talk to something else? And it's actually simpler than you think when you get into it. The nice thing about collectives is everyone participating in that collective is aware of what everyone else is doing. So node A is sending to node B, node B knows it's receiving from node A, and so on and so forth. So you kind of know at the beginning of a test, what all the patterns are. So all you have to do to make this work is your mocks need to do what the device under test is expecting. Basically, you just got to pass the duck test. From the accelerator under test point of view, if it looks like a duck, quacks like a duck, it must be a duck. So in this case, Keysight is a very expensive duck. I shouldn't be saying that. So Ashutosh will talk more about how exactly this works and some of the details of it, but think of it as a collectives emulator that can take input from our collective communications library and execute it in a similar fashion, okay? So now we're going to talk about some applications of this. This application we're going to talk about is measuring collective completion time. So one thing you commonly do in NPI is you'll measure the performance and just functionality, because sometimes just getting to performance is hard, of all-to-all collectives or some other collective with different rank sizes. In this example here, we used a fixed message size, so then the all-to-all size changes to correspond to that. And we evaluate it anywhere from, I can't read our first data point here, but anywhere from 8 ranks, 24 ranks, and so on, right? So with that, I'm going to hand it off to Ashutosh, who's going to go into more details of the results and interesting things we've discovered.
Thank you, Matt. So we have the accelerator and the NIC surrounded by the MOCs. So we usually care about 2 kinds of flows, right? Ones that originate from the NIC and land on the MOCs, which is NIC TX in red, and the ones that originate from the MOCs and land on the NIC, which is NIC RX. There's, of course, flows between the MOCs themselves, but that's not consequential for now. You see a green line, which represents the ideal trend as we go from 8 ranks all the way to 24 ranks, right? So there are 2 observations here. Let's first look at the blue one, NIC RX. We see as we go from 8 ranks to 24 ranks, we're able to achieve 90 to 97% of the ideal line rate, right? And the observation for NIC TX trend here is we see that there are some flows that are actually outliers, which is they unexpectedly achieve or exercise higher bandwidth rate than we expect them to, right? How do we do this? Green?
Green, yes.
Okay. So let's first look at the observation with NIC RX, which is the blue line, right, where we were able to achieve 90 to 97% of the ideal rate. Let's pick up the use case for 24 ranks, where we have 1 accelerator and NIC surrounded by 23 physical MOCs. All of them are 400 gig port speed. Now, since this is all-to-all, each MOC should be transmitting at 17.4 Gbps to the NIC, right? And based on the trend we saw before this, we're achieving around 97% of the rate, which is 17.0 Gbps. So what's going on? We did the capture on the NIC, which collects the packets coming from all the 23 MOCs, okay? And the first plot is basically the inter-arrival rate of packets coming from 1 such MOC, okay? So there, the threshold should have been 17.4 Gbps, but as you see, there are multiple instances where we go beyond the threshold, right? So definitely there is burstiness. This becomes more apparent if you look at a more cumulative representation of all the QPs and all the MOCs that are coming or landing on the NIC. And there you see the blue dotted line represents the inter-arrival rate, right? And the blue dotted line, again, you can see it goes sometimes beyond the green threshold, which is the 400 gigabits per second. We also overlaid the buffer usage, which is represented by red line. And as you can see, we do see an increase in buffer growth, but it's not enough to cause congestion, and hence we don't see any packet loss, right? But we do have a variation in the flow completion times. What you're looking at is the cumulative distribution function of the flow completion time, which is CDF. And ideally, it should be a vertical line representing that 100% of the flows achieved ideal line rate, right? But that's not the case over here. It varies all the way from 7.5 to 7.6 to 7.9 milliseconds. And in fact, 70% of the flows are actually taking higher than the ideal completion time we expect them to. Now, if we want to focus only on the accelerator, you want to take out the network switch and fabric from in between, we could actually do that with 1 physical MOCs, which is emulating arbitrary number of ranks behind the scenes, which we're calling virtual ranks, right? The idea behind this is you want to be able to find how the FCD trend projects as you go beyond 24 ranks, maybe 256, maybe something higher than that, okay? And again, as you can see from the plot, this trend looks very similar to the trend we saw with 24 physical MOCs. We're able to, we have the NIC TX, we have the NIC RX trend, and again, NIC RX, we are able to achieve around 97, 98% of the ideal line rate. And with NIC TX, again, we see an outlier, right? So what this tells us is we are indeed able to reproduce the variability when we use physical MOCs and when without virtual ranks, and when we use physical MOCs with virtual rank, right? And over here, again, with 24 virtual ranks and 256 virtual ranks, we have the same CDF that we showed before. If you look at the CDF shape again, you have the vertical line in between, and again, 70% of the flows are taking higher than the expected completion time. And indeed, there's still variation. So again, this adds on to the fact that we're able to reproduce the variability in the flow completion times. And we can do this for any arbitrary size, 256 virtual ranks, 512 virtual ranks. And let's quickly look at the outlier. This is something still investigation, work in progress. And this is for the NIC TX, the outlier that we noticed where we observe that the NIC is, where the flows originating from the NIC is actually, some of the flows are exercising higher bandwidth than expected, right? And if you look at the CDF, that vertical line that we're talking about, it's all the way to the extreme right? That means 99% of the flows are actually taking much less time than we expect them to. And if we plot the flow timeline where on the bottom, you have the start and end timestamp of each of the flows, you would definitely see that there are some flows that complete halfway through. So what's going on here, definitely we need to further investigate. But thanks to virtual ranks, we are able to reproduce this deterministically every time. So we're going to be on top of this and report back. Right?
So I just kind of want to summarize what we're talking about here, because we went through a lot in a short amount of time. We introduced the one-arm approach to sort of validating, I call it clusterless validation. Like if you make some assumptions that each of your devices is kind of behaving the same way, or you can even cycle through them, you can really reduce your test bed to something much, much less complex. You don't need to build a data center. And it sort of solves the chicken and egg problem. It's like, if I'm building a system and doing tests on a system, like how do I know it's good enough to greenlight 1,000 of them in a data center or even more? So I can just do that ahead of time. So I can really left shift all this work. Another thing I want to point out is like, it seems like this is fake and this is like, not real, but to the device under test, it has no difference. Like it can't tell the difference. Like we're showing just running our unmodified collective communications on one device under test. Like going forward, we're going to extend this to running PyTorch in full workloads. Because from its point of view, all the I/O looks the same, right? And the nice thing about that is we're not just testing the network. I know we're in the networking room. We're talking about validating networking. But there's way more to an accelerator than the network. Like how the HBM works, how hashing works for addresses, how power fluctuates. Like if you ever look at the power while an AI job is training, it's very spiky. And those spikes correspond to a collective finishing. So all those behaviors, all those dynamic behaviors are captured by this. So call to action. Up to date on this work stream, we focused a lot on the collectives. We have a good handle on the networking aspect. Like I know how to validate NICs at scale. I know how to validate like an embedded NIC and an accelerator at scale. But we want to take it more towards like the whole workload. So we need to kind of graduate from just looking at collective libraries to running it, the whole workload running PyTorch. With this technology, we can do it. It's just kind of on our backlog. The other thing is this whole presentation was about metrics from the network, metrics from the NIC. We should show the same for the GPU. Like we could show power, we could show how memory access is affected, all sorts of things. So I kind of see this work we're doing graduating from a networking project to really an AI systems project. Other thing I want to talk about is some standardization of this. I mean, honestly, like Ashutosh and I have been making this up as we go. So it works well with what we're doing, works well with what they're doing. This is a community. There's no reason we shouldn't be able to apply these same methodologies with a bunch of different accelerators, different NICs. I mean, there's nothing even Ethernet specific about this. This technique could work with anything. And that's about it. There's links from our last talk. You can talk to Keysight in the booth. You can reach out to us. Any questions?
Thank you.
Yeah, a kind of two-part question, I guess. So is this simulated data, or is this actually captured from your custom CCL library from an actual cluster that you're working on?
I mean, this is captured from actual hardware. There's no simulation in any of this data.
Okay, so you're actually using the collectives captured off a cluster.
Yeah.
Okay, cool. And I mean, you're talking about, some of the kind of community work here. I mean, it seems like this would be a fit with Chakra and some of the efforts in that space.
Yeah, that's sort of interesting. So 2 years ago when I talked about this, I said, yeah, Chakra is the way to get traces and feed it into this.
Yeah.
So, and that's kind of as we graduate from networking up to, the whole workload. So, a little feedback there. So I started this with Chakra, and we were using Chakra traces to collect it. But what we kind of found is PyTorch lowers like collectives differently depending on a bunch of heuristics and things built into the code, right? And because we don't have PyTorch yet, so what I ended up doing is capturing like a lower level trace, sort of right at the bottom of the collectives library and using that.
Okay.
There's no reason, I mean, this should be raised back up to Chakra, and maybe you can talk about Ashutosh on your side, because they use Chakra in part of their solution on this.
Okay, cool. It's good to hear they're connecting, so yeah, thanks.
Hey, so you partly answered my question. PyTorch uses or makes collectives behave slightly differently based on the workload. What other challenges would you anticipate when you move to looking at simulating workloads or much more broader based use case?
Honestly, the most difficult thing is getting everything to work in the lab. I mean, so, the test bed that I did 2 years ago was very complicated. I actually did that in a data center. This we did in a lab environment, and in theory, open source PyTorch and everything kind of works in the lab. In practice, it's very complicated. So sometimes it's just getting the software to work right. That's the biggest challenge, honestly. But assuming that it runs, I haven't seen a problem. I mean, we're not talking about it here, but I've done some POCs that shows that it works.
Thank you.
I guess I'll share something that is important is like, depending on the workload. So the thing about this is all just synthetic data. When you're doing collective benchmark, you don't care about the data. The tensors just have to be the right size. Depending on the actual AI model, it might or might not care about the data, just so it doesn't crash. For example, like if you're doing like an all reduce, you can send zeros, the gradients will reduce fine. But let's just say you're running a recommendation model, and where your embedding tables are sharded and you're changing data, like you have to have valid indices into the destination embedding table. So like depending on the model, and if you want to like not change things, the content of the data does have some significance.
Hey Matt, great talk. So quick question, this approach, what was the similarity and fidelity if you compare with a real final fleet?
So, I mean, the honest answer is I don't have, for this particular hardware under test, I don't have 256 of them to tell you. But for small numbers, it correlates very well. So that would be a good thing to share. It's like, okay, once we have a data center built, correlated back to this, and it should match. What isn't captured here that probably will happen is some of this is, a lot of times when you do benchmarks, you kind of assume that like all your ranks enter the collective at the same amount of time. You might put a barrier before it. But when you're doing an actual workload, you enter the collective whenever the compute portion before that is finished. So at scale, usually what we see is a lot of skew between when different ranks enter the collective. So that wouldn't be captured here, so that's probably something we kind of want to back annotate, just whatever the relative skew is and then feed it into here. I would expect very high correlation, but we can come back and talk about it if people are interested next year.
All right, thanks a lot, Matt and Ashutosh.
All right,
Really
thank you.
interesting talk.
Thanks.
Thank you.